In this presentation we're going to look at recurrence relation and then later on a proof by induction. So here we have u of n plus 1 is equal to u of n plus n, and the initial condition is u1 is equal to 0. Now it asks us to calculate u3, u4 and u5. So first off, let's just draw up a little table. There we go. And so just like that, and we're going to have n on this side. N equals 1, 2, 3, 4, 5. And here is u of n. In the first case it is 0. Okay. In the second case we're asked for u of 2. Now u of 2, so u of n is u of n plus 1. Oh, let's start little typo there. So u of n plus 1 over here. Let's add this column here. It actually makes things much easier. This is equal to u of n plus n. So this is equal to this value here plus that value there. And that is equals 0 plus 1, and in this case that's equal to 1. So the next value for u is u of n plus 1, and that's equal to 1. So let's put that there. U of n plus 1 is equal to u of n, which is 2, no, it's 1, plus 2. And that gives us 3. Here we have 3. The next value is going to be 3 plus 3. That's equal to 6. Have 6 there. Next value is 6 plus 4, and that's equal to 10. 10 goes there. Next value is 10 plus 5, and that's equal to 15. So those are the values there. 0, 1, 3, 6, 10, and so on. We weren't actually asked for 15, but I just done it for the sake of completion. That's equal to 6. So these are the values actually we're asked for in particular: 3, 6, and 10. Okay, now what we're going to do now is a proof by induction question. So let's remember this part here. U of n plus 1 equals un plus n. Okay, because that is always helpful when we do induction questions, proof by induction questions. This is the proof by induction question. Show that un equals n times n minus 1 divided by 2. Okay. Given the previous expression. So the first thing is first step is base step. There's 3 steps here. Show this for n equals 1. Okay. So for n equals 1, does this hold for n equals 1? In n equals 1, u1 is going to equal to 0. Now let's just check this to see, does that confirm? U of 1 is equal to 1 times 1 minus 1 all over 2. 1 minus 1 is 0. 1 times 0 over 2. That gives us 0. That's fine. Okay, works there. We're going to do the induction hypothesis now. That's the second step. And I'm just going to do a very quick example because it's not really essentially just state this case here. U of k, we're going to assume this is true, equals k times k minus 1 all over 2. Okay, so we're going to assume this. Now I'm running through it very quickly. You should put more effort into your answers than I'm doing here. I just try to cram this all into one page. Now, induction step. Demonstrate that this holds for k plus 1. So u of k plus 1, that's going to be equal to k plus 1 times k. Let's just show where we came up with that actually. let's just do it as a side note up here. Let's do it in green. For u of k plus 1, so that's k plus 1 times k plus 1 minus 1 all over 2. Simplify that. You have k plus 1 here minus 1. That just simplifies to k. That's why what we have down here. That there is equal to k plus k squared all over 2. Now, what we have to do here is show how this works for show that this holds, that this is consistent with what we have elsewhere. So what we're going to do here is go back here a step. This essentially, our argument here is this is going to be equal to u of k plus k. So we have to sort of demonstrate that. So let's go back here to this one here, and this is equal to k squared minus k all over 2. Okay. And what we're going to do here is look at the difference between the two. And so let's do it up at the top here. K squared over 2. Actually, let's do that again. K squared over 2 plus k over 2. I'm splitting this up into two parts. And that's the first part there. That's u of k plus 1. Minus this. So it's k squared over 2. And minus k over 2. Okay. Now this part here minus that part there, that cancels out. So we're left with k over 2 minus k over 2. That's equal to k. 2k over 2, that's just equal to k. So the difference there is k. And as a result of that, we can show that that is equal, in fact, equal to u of k plus k. And that is our hypothesis, proof by hypothesis worked out. Essentially, the key part there is actually just looking at the difference between. I'll actually just make a quick more. This is u of k plus 1 minus u of k, and again that's u of k plus 1, and this is u of k, and we're subtracting the two, and we find that the difference is actually equal to k. So that ends that presentation.